In this video, we're going to look at how to use the formal definition of the limit to explain how this limit, or if this limit exists. So we want to prove it using the formal definition, and then we're going to explain or look at it geometrically to kind of like formalize or ground our understanding in a combination of both algebraic completeness, but also just geometric understanding in general. The combination of the two, I think, is powerful to have an intuitive sense, but also like a foundational sense in the sense of like an algorithm. So what do we want to show? So the main idea here is to show from the formal definition that for all x, not all x, sorry, for all epsilon greater than zero, means that an epsilon can be any value. So we want it to be true for any epsilon greater than zero. When we're saying that, there exists a delta greater than zero. So given any one of these, there's always going to find a delta greater than zero, such that the distance f of x minus the limit is going to be less than epsilon whenever the following condition is held. Whenever 0 is less than or equal to x minus c, the point that you're taking the limit at, is less than delta. Okay? So from our class discussion, one way to think about this is that we want the distance, because the absolute values are distance of f of x minus L being less than epsilon. Whenever this is true, okay, we want to find whenever this is true, I don't want to write a bunch of words, but whenever that's true, we want to find a value for delta, find a delta that makes it true or satisfies the distance. Okay, so I'm going to switch just for a second to a geometric view. I'm going to have us explore this idea a little bit more from the perspective of a graph. And so let's take a look here. So here's my function, f of x. You can see it labeled down here. It's the square root of x minus 5. And so as we go along this route, here at the point x equals 9, this is the limit that we're looking for. And this function is defined here. And we could even say that it's actually continuous, though we haven't talked about that specifically yet. But you can see that the value is, and so normally we would just plug in the value of 9, and we would subtract 5 from that. Square root of 4, which is the difference of 9 and 5, is equal to 2. And that's what we're trying to show. But that's plugging it in. That's assuming that the limit exists. And so we're trying to figure out how do we show this in a formal setting. Okay. What we're looking at, realistically speaking, is okay, here's my delta range. Okay, or sorry, my delta range, my epsilon range. And epsilon can range for any number. So I have it set here. It's equal to 0 all the way up to 3 as the range of epsilon that I chose. Okay, and they're skipping by half. So no matter what it's saying is that no matter how I choose to make this, whatever value I choose to make epsilon, I need to find a delta. I need to find a delta value that makes it true. Okay. Now, it could be the case that delta is really small, right? In which case I have a very narrow range of making that true. Or it could be the case that delta is really big, in which case it's most guaranteed to be true. So, but this delta existence really depends on every epsilon value that we can possibly make. So we have to kind of figure out how to make this distance. Now remember, we have a line y equals 2. This is the limit that we're trying to approach. This value here is the one that we're really trying to build around. And so this epsilon, this arbitrary epsilon, is going to shrink and grow around it. It needs to be true. This inequality needs to be true. In other words, we need to find a delta. This purple box needs to be true no matter what value of the epsilon, the green box that we find. Okay, so we're really looking at what forms kind of like this square, or not square, this rectangular shape. We're really trying to figure out, given the height of this rectangle, right? How big does my width have to be to make that area make sense? Okay. So that's really what we're trying to do. That's the struggle that we're trying to figure out here. Okay. So let's switch back and do some algebra now that we have a little bit more of an intuition, maybe, um, of the type of geometry that we're dealing with here. Okay. All right. So we're going to explore this idea a little bit more. So notice that our limit is here is 2. This is our f of x, and this is the c value that we're approaching. So let's go ahead and plug in the values just to kind of make it look a little less scary. So f of x here is going to be the square root of x minus 5. And the limit is 2. So we want this to be true. So we want that to be less than epsilon whenever 0 is less than the absolute value of x minus the limit, which was 9, is less than delta. Okay. So this is the statement here. This is the formal statement that we want to show. Okay, so this statement right here is really what we're after. So we have to figure out how to make this comparable to this, so that way we can find if that delta actually exists. Okay. And so since there isn't a simple way to make this algebraically look comparable to this, we're gonna suppose we're gonna just choose an epsilon equal to 1. Okay. And what that means is that this value here then is always, we're looking for the values that are always less than 1. Okay, so if we switch back just for a second to the geometric point of view, just to keep this in mind, okay? Just kind of give you an idea of what I mean here. So let's choose epsilon equal to 1. Okay. And so you're going to see then, if we look at the function here, epsilon equal to 1 gives a pretty large value range. And so we're going to see if, and this is possible because our function f of x is very slow and it's monotonically increasing on this interval, actually for all values. So there's a lot of nice properties that this particular f of x has that allows us to say, all right, let's give this a try. Okay, and so we're going to try epsilon equal to 1. It's a completely arbitrary choice, but that is a good one to generally utilize in situations like this. All right, so let's switch back and take a look. And so what we're trying to do is trying to figure out what size of the sides of our box do we need in order for this thing to be guaranteed to exist. Okay, and so let's figure that out. Okay, so if this is true, if we're going to suppose epsilon is equal to 1, okay, remember epsilon, it's true for any of them. So let's just choose one. And let's say epsilon is equal to 1. Okay, then that means that the absolute value of the square root of x minus 5 minus 2 is going to be less than 1. Okay, well, I can do a little side work here, and I know that this is going to be between -1 square root of x minus 5 minus, oh, it's a minus 2, sorry, is less than 1. So dropping the inequality, we have a bounded interval here. So here's the bounded interval, dropping the absolute value. And then I can move this -2 out by adding 2 to all of the sides. And so this becomes a positive 1 is less than the square root of x minus 5 is less than 3. Okay. And then I'm going to, since they're all positive numbers, I'm going to square this interval, and I get 1 is less than x minus 5, which is less than 9. Okay. And then last but not least, I can now add 5 across each of these without changing anything. And so I get the 6 less than x less than 5 plus 9 is 14. Okay. So this creates then the range, well, actually be kind of like the domain, that would guarantee that our domain or that our range would be less than 1. Okay. In other words, if we think about a numerical interval, I'm trying to think of where to draw this line. I'm going to draw it right below it. Okay. Let's get this up a little bit. Okay. So if this is 6, and over here, 7, 8, 9, there's our point, 9. And we don't know if it's defined there. So we have an open interval here. 10, 11, 12, 13, 14. So here's my 14. There's my closing interval. That should have been like this. Okay. What we're saying is our range here, okay, that was up here in the graph. If we project down, what we find is that this is the domain values. Okay, so this would be like the x-axis. Okay, so we found the length of our box that our interval would have to be in around this value. Okay, around this limit. In other words, the height of the box with this epsilon. Okay, we've defined the height, and now what we've just found is how wide the box has to be. Okay. Now remember though, we want it to be true regardless of what epsilon is. Okay. And so if we look here, if we look at the distance between our point of interest, which is, remember, we're taking the limit at 9. So this is where we're taking the limit at. Okay. Then we want to look at our possible choices for delta 1 and delta 2. Okay, this delta is a distance of 3, and this delta is a distance of 5. So if we choose delta equal to the min of the set delta 1 and delta 2, okay, well, clearly 3 is less than 5, so delta 1 is our choice. So choose delta 1, okay, which is equal to 3. Okay, and if we keep that delta, then we're guaranteed that we have a delta that no matter what, we're going to be able to find that epsilon for 1. Okay, and so what this says is then that 0 is going to be less than the value of x minus 9 whenever delta is less than 3. If that's true, then the limit will exist. Okay, so finally, then we can write for this that for the square root of x minus 5 minus 2 less than 1. Again, our choice of epsilon, we had to choose that to be true, is true whenever 0 is less than the value of x minus 9, which is less than 3. That's supposed to be 3. That's the delta that we found. Okay, so let's switch back real quick to the geometric perspective and see if this intuition settles with our geometric understanding. So look, if we look here, trying to make it a little bit bigger. Okay, so if we look here, so here is our 9, right? This is our vertical line. This is the point that we're interested in. Okay, and we set epsilon equal to 1. Okay, and you can see then that the height of the rectangle goes from our limit value, which is 2, up to 3 and down to 1. That is and so what width do we have to create? Well, if we choose delta equal to 3, look what happens when delta is equal to 3. Okay, you'll notice that the side of the box comes down to the intersection point here at 6, and at the minimum value of the limit, aka epsilon equal to a -1, right, down here. So that forms the lower left-hand corner of our box. Okay, and that happens to be the minimum distance that we need. Now look, if we choose to have our delta go to 5, the other endpoint, I'm sure you can predict by now that the value here of this size of the box, look, is at the exact point where this is at x equals 14, this vertical line, and that's the exact location of where our function exits the box created by the height of epsilon equal to 1. Okay, so the size of the box goes from 3 over to 5, so it kind of creates this lopsided. And so which one do we need? Well, we want the smallest of the two that will guarantee that this is going to be true. So 5 is big. It definitely makes it true, but there's a one that's smaller, that'll give us the same result, namely when delta is equal to 3, you see that we have in here then a box size that will guarantee for this delta that we have around the point 2. For this delta, we will always have an epsilon. Sorry, for this epsilon, I said that backward. For this epsilon, we can find a delta that satisfies this condition. All right, I hope that was helpful, and I'll see you in the next video.